Anybody got any questions? So our next test is a week from Monday, right? So the formal announcement, of course, is always a week before, but it is that Monday of Thanksgiving week. I'll get your room numbers to you by Monday so that you know where you're going for our last test of the semester. And that's it for announcements. All right, so let's pin this and get started. We've got some fun stuff to do tonight. Okay, so we are going to finish what we're going to do in section 6.1. We're going to look at big unions and intersections. I call them big because they have indexing, the same way summation and product notation has indexing. And we'll be focusing on interval notation. We're going to do a warm up with interval notation. Then we're going to look at what disjoint sets and pairwise disjoint sets are. In fact, we'll probably do that first, and then we'll get to the unions and intersections. And then we're going to wrap up tonight with the idea of a partition. A partition is a very important concept. It's when we have a set and we split it up into a bunch of subsets, but they're very special. None of them can be empty, and their union has to build the set back. The other thing is they can't have any elements in common. So it's a real way of splitting up a set into subsets that rebuild the set if you take their union. So that's what's on the menu for tonight. So our do now problems are the do later from last time, from the day 20 lecture. So let's go ahead and do those now, because I want to make sure that you actually do go through these. So let's take a look. These are all interval notation problems, and I want to emphasize something, folks. When we have interval notation, there are an infinite number of numbers in an interval that's a real interval. I may use integer numbers as the bounds, like -2 and 3, but this set contains a lot more than -2, -1, 0, 1, 2. This set contains an infinite number of real numbers. Every rational and irrational number between -2 and 3, including -2, not including 3, is in this set. And that's the same way with all of these, okay? It's a very rare time where interval notation indicates a finite set, and that's a very special case, and we'll look at that tonight. So for the first one, a picture can really help. So if we want to understand what the intersection of these two sets is, it can be very helpful to draw a picture. So here is a picture of the set -2, 3, where we're including the -2. We indicate that with a square bracket. But we're not including the 3 because this is a soft parentheses. It's the soft bracket. It says it's like having an open hole at the 3. Everything in between there is being included. -1, 4 as a set, well, we're not including the -1. We have a soft parentheses there, but we are including the 4, which is indicated with the square bracket. And of course, intersection is the operation that is the and operator for sets. We're looking, it's like the intersection of two streets. That intersection is part of each of the streets. It's in both streets. So we want the elements that are in both of these sets. And, I've kind of shaded here with red to indicate, yeah, these are the elements that seem to look like, they're in both sets, but we have to think carefully about the endpoints because we can only include an endpoint if it's part of both sets. Well, the left endpoint is -1. See, that's the overlap here. It's not part of the set on the right, -1, 4. So we can't include it in the intersection because it's, even though it's in the set on the right, -2, 3, it's not a part of the set -1, 4. So we cannot include -1. So we put a soft bracket there. Same way with the 3. The 3 is not part of the first set. Even though it is an element of the second set, it still doesn't get to be in the intersection because it's not part of both of the sets. It's not an element of both sets. So the answer is, using interval notation, everything strictly between -1 and 3. And again, I just want to emphasize that's an infinite number of real numbers in there. It's not just 0, 1, and 2. It's all the real numbers, as many as you can imagine, sitting in here in this area of the real line that is shared, that is overlapped between these two. Any questions? All right, so let's continue with this now. Union, let's review union. The union of two sets is the set of elements that are in either or, so either in this set or in this set or in both. It's the inclusive or. So it's like the union of two people in a marriage. It's bigger than either one of the people. It includes, everything they have in common plus the individual people, right? So union, builds something that's bigger than either set by itself, unless one of the sets is actually a subset of the other. So see if you can draw a picture that would indicate how to do the union, or you can just look at this picture and ask yourself which elements of the reals are in either -2, 3, or in the set -1, 4. Anybody want to take a stab at it?
The set -2 to 4.
And are we going to include -2?
Yes. Include, yeah, -2 and 4, right?
That's right. We're going to include -2 because it's part of one of these sets, and we're going to include 4 because it's a part of the other set. And all of the things in between are included because, there's no gap. There's no gap between these two sets. These two sets actually have quite a bit of overlap. So that's exactly right. Let's go ahead and start a new sheet here. And let's write that. So for B, when we take -2, 3, soft bracket there, union, soft bracket -1, 4, square bracket, when we try to figure out what that is, well, it certainly is equal to the set containing -2 on the left bound all the way up to and including 4. Any questions on that, folks? Okay, part of the instructions, of course, were that the universe is the reals, and we may have to use union symbols sometimes. But I don't think we have to use a union symbol on C, but we are going to have to use a union symbol eventually here. Let's look at the answer to C. All right. So C says we want to find the complement of the set 5 to infinity, and we're not including 5. By the way, folks, infinity is not a number. It's not something that we could, include as an end point. Infinity is the concept that this keeps on going forever to the right. So if we drew a picture of this set, here's 5, say, well, we're not going to include the 5 because we have soft bracket 5, but it's all of the numbers to the right of 5, that are bigger than 5. So we can just shade this whole area, and that would be a good representation of the set 5 infinity. Remember what the complement is. The complement is the set of elements that are in the universe, but not in the set. So we are thinking about which real numbers are in the universe of the real lines, but are not in this set. Anybody want to take a stab at it? The numbers that are off this way. I guess the real question is about this boundary. Are we going to include 5 in the complement set or not? What do you think?
No.
Okay, so let's think about it. Is 5 an element of the set in blue, the original set, 5 to infinity?
Yes, so you wouldn't include it, or
Yeah,
you would include it.
well, is 5 an element of the original set from 5 to infinity with the soft bracket here?
No.
No, since it's not in this set, then it is in the complement. So we do include the 5 because it's not a part of the set that's getting the complement taken of it. So we would indicate this as negative infinity. Of course, it's a soft bracket there, up to 5 with a square bracket. Questions? Okay, so our next one, D, is also a complement. Okay, but the set that we're taking the complement of kind of sits, well, not exactly in the middle, but the real number line doesn't actually have a middle anyway. But it's negative 6, 7, square bracket, complement. So if we draw this set, negative 6 to 7. So here's negative 6, and let's say here's 7. And it's square brackets. So it's everything between negative 6 and 7, but also including negative 6 and 7, right? So we want everything that's not in here. Well, we've got stuff coming out either side, right? We've got real numbers that are bigger than 7. We've got real numbers that are less than 6. The question is about the boundaries. When we start to build the complement set, should we include negative 6?
No.
No, why not?
Because it's included in the original set
Yeah,
here.
negative 6 is part of the original set, so we can't include it in the complement. So it's a soft bracket there. And what about the 7? Should we include the 7 in the complement set?
No, because it's
It's
also in the
That's
original.
right. Exactly. Very nice. No, for the same reason. So when we write the complement set, it's going to be from negative infinity to negative 6. Don't include the negative 6. Union 7 to infinity. Again, we don't include the 7. Questions? And finally, our last do now is just to practice set difference. And remember what the algorithm for set difference is. The algorithm for a set A minus B is start with the elements in A and then subtract away any elements from A that are also in B. So we want to literally subtract this set B away. And I put pi here just as a way to remind everybody that even though I'm using a lot of integers as the boundaries of these sets in this do now, they are not the only elements that are in these sets. So let's do E. Again, pictures really help. So, if we draw a picture from negative 4 square bracket, say to pi, square bracket, right? So negative 4, negative 3, negative 2, somewhere, zeros in here, a little closer to pi than negative 4. And then like here's negative 1 and here's positive 1. This first set includes the negative 4 and the pi. So it's all of this. But what we want to subtract away is the set that lives between negative 1 and 1, but doesn't include negative 1 or 1. So it's soft brackets, right? So what we're really looking for is we're looking for the elements of this set that would be left over, from negative 4 to pi, that would be left over if we subtracted away the elements there in the middle. Here's negative 4, here's pi, right? So we look to keep everything that's in the set from negative 4 to pi that's not between negative 1 and 1. So it's kind of like that area that we're going to keep. But we have to think about the bounds. We have to think about what's happening at negative 1 and what's happening at positive 1. Are they going to be part of the complement set or not? Okay, so should -4 be part of, I said complement set, excuse me, the set difference. Should -4 be part of the set difference?
Yes.
Yes, because it's right there and it's not part of what we're subtracting. So we definitely want to include the -4. Now, so we're going to include all of these, and then we start subtracting right around here. Now, should the -1 be in this set difference or not? Should we include the -1 in the answer?
Yeah.
Why?
Because with the set -4 to pi, -1 to 1 is being subtracted, but -1 and 1 aren't included.
That's right. -1 and 1 are not parts of this set that we're subtracting. So we're not going to subtract away -1. And for the same reason, we're not going to subtract away 1 either. So it goes from -1, excuse me, -4 to -1, square bracket on both sides. And then we'll union that with the set that starts on the other side here at 1, include the 1 with the set we're building because we're not subtracting it away because it's not in this set that we're subtracting away all the way up to, and of course, we're going to include the pi. So it's square bracket 1 to pi square bracket. So we need to use a union because the red set that I've shaded here is the set difference that we're looking for. And, elements can't be in both. They're either, X is either over here or over here, if it's in this set at all. Questions? Okay, good. So that's a good warm up. Now let's talk about the two definitions that we need to have tonight. And the definitions are for disjoint sets and pairwise disjoint sets. It's real simple. Disjoint sets have no elements in common. If you intersected them, this intersection's empty. And pairwise or mutually, you can say it either way. You can say pairwise disjoint sets, or you can say mutually disjoint sets are sets that don't have any elements in common. If you take any two of the sets in the collection, they're pairwise disjoint. So here are our definitions. Given sets A and B, we say A and B are disjoint. That's what we're defining, what it means for them to be disjoint. If A intersect B is equal to the empty set. Remember the symbol for the empty set? It looks like almost like a computer science 0, but not quite. It's rounder. Remember, that's our empty set. There's nothing in there. So we can even say that, i.e., A and B have no elements in common. And then the definition for pairwise disjoint sets goes like this. Let's give ourselves a bunch of sets. So given sets, we'll say A1, comma, A2, comma, dot, 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 up to say A sub K. This could even be an infinite collection. We say the collection, we'll call it curly C, which is the set of these sets. So curly C is a collection of these sets. We often use curly names for sets of sets, is a collection of pairwise disjoint sets or mutually disjoint sets if And here's the way we try to say that if you take any two of them and look at their intersection, that intersection is empty. We say that mathematically, AI intersect AJ is equal to the empty set whenever I is not equal to J. That's the way that we mathematically say a collection of sets have no elements in common pairwise. Just take any two of the sets as long as they're not the same set. And that's what I not equal to J means. It means, hey, if the indexing numbers are different, like A1 and A2, if you intersect A1, intersect A2, you'll get empty set. Or if you take A1, intersect AK, you get the empty set, or A2, intersect AK. You get the drift. If you take any two of those sets, their intersection is empty. Okay, so that's what it means for sets to be disjoint or mutually disjoint, pairwise disjoint. Okay, so now we're going to use this definition here in a minute while we look at indexed unions and intersections. So that's our next topic here. I'll call them big unions and intersections, but what I really mean by big is indexed. Big unions and intersections. In other words, indexed unions and intersections. And these indexing features are the same as the kinds of indexing features we saw with products and summations. The indexing variable always represents an integer, and we increment as we, run through the variable. It starts at some lowest level, and we increment by +1. We just, add one, add one, add one. So here are our definitions. We've got several. Let's talk about unions first. Given sets A1, A2, dot, dot, dot. I want to indicate this could be an infinite collection. We define the indexed unions. There's several of them that we're going to look at below as indicated. Okay, so the union, say from I equals M to M, so same lower bound and upper bound of A sub I. Well, same way with what we saw with summations. If the lower and upper bounds of the indexing variable are the same, it's just that single set in the case of set notation. It's just that one set, A sub M. But if M is less than or equal to N, we could say the union from I equals M to N of the A sub I. Well, that's when we say, oh, okay, the first one would be A sub M union. The next set would be A sub M plus 1. We increment our indexing variable by 1, even if it's for unions. Keep on going. And the last set we union together with all these other ones is A sub N. So start at M, end at N, just like you think we should. And then if we want to perform an infinite union, so from I equals, say, M to infinity of the A sub I, that union from I equals M to infinity of the A sub I, well, we start with A sub M, union A sub M plus 1, keep going, union A sub M plus 2, union, and then we just put dot, dot, dots, and that just means that union keeps on going forever. And we will look at plenty of examples tonight, okay? It's the same deal with intersections. Given sets A1, A2, dot, 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 we define the indexed intersections below is indicated. And we'll do the same three things. If we're just intersecting from I equals M to M of the A sub I, that's that single set, A sub M, just like you think it should be. If it's the indexing of the union from I equals M to N, where M is less than or equal to N of the A sub I, well, that's A sub M intersected with A sub M plus 1, intersected, keep on going, intersected A sub N, and then the intersection from I equals M to infinity of the A sub I is, of course, an infinite intersection where we start with M. So it's A sub M, intersect A sub M plus 1, just keep on going, A sub M plus 2, until you've shown enough of the pattern to indicate, hey, it just keeps on going the way you think it should. So this notation should seem fairly natural, considering the fact that we've seen indexed products and summations. And since we've also seen union and intersection symbols, this should come fairly naturally. So there are some fun applications of these types of problems involving these indexed unions. And let's play those games. I've got 2 or 3 examples laid out for you here. So here's some practice. So this is our example 2. I guess our do now was our first example today. Example 2, we're going to define, and this is the fun part. You get to think a little bit. A sub I to be equal to the following interval, square bracket 0, comma, I, soft bracket. And this is for I equals 1, 2, 3, dot, dot, dot. Okay? So for positive integers, I. A, find each set and write your answer using interval notation. Okay? All right, 1. The union from I equals 1 to 5 of the A sub I. 2. The intersection from I equals 1 to 5 of the A sub I. 3. The union from I equals 1 to N of the A sub I. 4. The intersection, I'm going to go straight to the union from I equals 1 to infinity of the A sub I. 5. The intersection from I equals 1 to infinity of the A sub I. Now, it really is helpful to see some pictures. So I've got a separate page of notes that I drew up, and I just want to show you what these might look like. It can really help. So the A sub I is defined as the set from 0 to I. Okay? So A sub 1 is indicated here in blue, where it looks dark. And here it is shaded from 0 to 1. We're including the 0. It's a square bracket 0. So this is a square bracket. But we're not including the 1. Okay? A sub 2, well, I is 2. So we put 2 in for I. And it's this red region We're including the 0 because it's a square bracket, but we're not including the 2. So we have a soft red parentheses there for the 2. A sub 3, right? I is 3, so it's from 0, including the 0, up to, but not including 3. That's in green. So I've drawn 4 of them. So A sub 4 goes from 0 to 4, but doesn't include the 4. So a picture can really help as we start to try to think about. So the union from I equals 1 to 5. Okay, so I didn't draw A sub 5, but I think that you can imagine where it is. So if we took the union of these sets, we're asking for the set of elements that is in A1 or A2 or both or A3 or A4 or A5. So so literally this is 0, 1, soft bracket union, 0 to 2, soft bracket union, 0 to 3, soft bracket union, 0 to 4, soft bracket union, 0 to 5, soft bracket. So what is that union? Anybody?
Bracket 0 to 5, not including 5.
That's right. Square bracket 0 to 5, we don't include the 5 because there's no space between these. It's not like we're losing any of these real numbers. We're getting them all the way up to 5, but not quite 5. All the way up to, but not including 5. Okay, good. Now, see how much a picture can help? Picture can be very helpful. What about the intersection of those same sets? We're asking for the X in the reals that are in all of the sets. We want the X to be in A1, and X needs to also be in A2. And remember, it's the and operator. X needs to be in A3, and X needs to be in A4, and X needs to be in A5. So which elements appear in all of these sets? These are nested sets, actually. They have kind of an interesting property where each set is contained in the next one. A sub k is a subset of A sub k plus 1. So that makes it kind of interesting. Somebody else want to chime in besides Edwin? Open the chat so I can see it. Anybody? What's the intersection? The X has got to be in all of them. So I have a different picture I'll show you. Here's a different picture. Here's A1. I've stacked them up here. Here's A2. Here's A3. And I've tried to kind of show the region where there are X's shared by all of these sets. Do you see it? And zeros in every single one of these sets. Do you agree that we can definitely include 0? But we can't include 1 because it's not in the first set. But 1/2 is in all of the sets, and 2/3 is in all of the sets, and 4/5 is in all of the sets, and 99/100ths is in all of the sets. In fact, everything up to and not including 1 is a part, a real number in all of these. So is in the intersection. Does that make sense? Kendall, does that make sense? Who all's here? We got Kendall here, Danny's here, Nick is here, Eric is here. Ronnie's here and Edwin's here. We got a small group. Okay, I'm not hearing much, so I'm getting crickets tonight, so I'm gonna assume that makes sense. All right, so what if we took the union, folks, from I equals 1 to n? Let's just think about that. It would be 0, 1, union, include 0 to 2, don't include 2, union, keep on going all the way up to a sub n, which means just put the n into I. A sub n is just include 0, go up to n, but don't include n. So that's what a sub n looks like. So what would be the union of those? I mean, it looks a lot like this. It's just instead of 5, we've got n. We don't know what n is. We just know it's, bigger than or equal to 1.
0 to n,
Yeah,
including 0 and not including n.
exactly. Perfect. And what if we take the union forever? So it's 0, 1, don't include 1, union 0 to 2, union 0 to 3. But now we just say, hey, this union keeps on going forever. It's unbounded. So, if you look at this picture, just imagine that we just keep adding. There's just more and more sets that we keep unioning to this. What would that union look like?
0 to not including 0, not including infinity.
That's right. And folks, even if this set was defined with a square bracket here, we never would use a square bracket if we had infinity or negative infinity. You never use a square bracket because it doesn't make sense to think about including infinity as an endpoint. That's what square bracket means. It means, oh, we're going to include that particular point as an endpoint. There is no endpoint. Infinity is not a number. It's an idea. It's just the concept of keep on going to the right forever. What about if we did an infinite intersection? What would what would that calculation look like? We just does it really help us out to keep intersecting with more and more of these sets? Is it going to make that intersection any bigger than it is? Generally, adding more and more sets to an intersection would make an intersection smaller and smaller. But in this case, because these are nested, what is the intersection of these?
0 to 1.
Yeah,
Not
it's
including
still
1.
0 to 1. It's very much like what we got when we didn't know how far to the right we were going. We're still bound up by the only elements in common to all these sets, which is what the intersection means, are the elements in that first set, A1. Okay. And the last question that you're going to see, and you're going to see the picture. I mean, this is what the Post-it notes look like, okay? But the last question I'd like to ask you is just this question. Are the A sub I pairwise disjoint or mutually disjoint? Are they mutually disjoint? It can help to look at a picture. Mutually disjoint means if you take any two of them, any two, that they would have an empty intersection. Is that true for these?
No.
Not at all. In fact, we intersected an infinite number of them and got A1, So these are definitely not pairwise disjoint. You take any two of these and you're going to have an intersection that's non-trivial. All right, let's look at another example. Example 3. Okay, so we're going to define B sub k now to equal the square bracket negative k to k square bracket, and this is for k equals 0, 1, 2, 3, keep on going. So we're including 0 as a possible indexing number because I want to show you something about what happens when we have square bracket 0, 0. Okay, so find each set and write using interval notation. Same instructions as before. We're practicing using interval notation. Okay, A. The union from it's K, excuse me, from the union from K equals 0 to 3 of the B sub K. B. The intersection from K equals 0 to 3 of the B sub K. C. The union from K equals 0 to N of the B sub K. D. The intersection from K equals 0 to N of the B sub K. And then we'll do E and F will be the infinite ones. The union from K equals 0 to infinity of B sub K, and the intersection from K equals 0 to infinity of the B sub K. The last question will be, are the B sub K pairwise disjoint? Okay, so we'll slide it up. But that's the last question. Are they pairwise disjoint? So again, it can be really helpful to draw a picture. So I've got kind of the separate page of notes. Let me show you the picture that I've drawn for the B sub K. Okay, so the kind of interesting set in this whole group is B sub 0, because what that means is we're going to put 0 in here and 0 in here, but negative 0 is just 0. So this is square bracket 0, 0. So we're including 0, but that's all that's there. See what I mean? So this is actually just the singleton set just containing the number 0. So it's interesting. B sub 1, so when K is 1, it's the set between negative 1 and 1 inclusive. That, include the endpoint. So square bracket negative 1 to 1. So that's here in blue, this dark one. The red set B sub 2 is from negative 2 to 2, inclusive. So I've tried to indicate there. And then B sub 3 is from negative 3 to 3. These are also nested sets. B naught is contained in B1, which is a subset of B2, which is a subset of B3. So these nested sets make kind of interesting examples to look at. So with that in mind, what is the union of from K equals 0 to 3 of the B sub K? Well, it's, negative 0 to 0, which is just going to be 0, union negative 1 to 1, union negative 2 to 2, union negative 3 to 3, where we're including the endpoints in all of those. So what is that union, folks?
Negative 3 to 3.
Yeah, negative 3, include the endpoints, obviously, to 3, right? I mean, this green set includes all the other ones. So the union is this biggest one. What about the intersection from K equals 0 to 3? So now we're trying to find elements that are common to all of these. Any element in this intersection has to be in every single one of these. Like it's, these, like negative 3 is not in B sub 2, and negative 2 is not in B sub 1, right? And negative 1 is not in B sub 0, right? So what, if any, real numbers are in all 4 of these?
0.
Yep. I'll write it like this, but it's kind of silly to say negative 0, but that is the set from 0 to 0, which we just can write as the singleton set 0, or you can write it like that. Either way is fine. You'll see some of these in the WebAssign that's up and due Sunday. So this is practice for your WebAssign, to be honest. What about the union from K equals 0 to N of the B sub K? We can see what this looks like, it's, we're going to start unioning these up. And then we're just going to say dot, dot, dot. Finally, union. Well, when K is in, we just put negative n as the left bound and positive n as the right bound. So what's the union of those? Just imagine this keeps going out and out and out to some value n.
Negative in the end.
Yep. Does everybody understand? Everybody's kind of quiet tonight, except, okay, good. Thanks for shaking your head, Kendall. You know, I understand it's cold tonight. You know, the weather's changing. It's kind of hard to get into the swing here. So thanks for hanging with. What if we intersected all these, including negative n to n? Is that going to change? Adding more and more and more, does that really help with the intersection? Nope. It's still just going to be the 1.0 to 0, or, just the singleton set with 0, right? So what about the union forever? The union from k equals 0 to infinity of the b sub k. So this is union. So something does happen when we add, more sets to a union, especially a union where it looks like this, where it just says, hey, we're just going to keep going forever and ever. What would that union look like?
Negative infinity to infinity.
And we do not use square brackets, folks, because negative infinity can't be included. So even if the definition says square brackets, if it's infinity or negative infinity getting involved, you use soft brackets, okay? And it's the same way with this intersection as it was for the other intersections. I could put negative 0 here. I think in the notes I put negative 0, but, come on. It's just 0. It, doesn't really help us to keep on adding more to that intersection. The bottom line is the only element that's going to be in all of those. It's just, oops, not 1, 0, my bad. The single number 0. So are the B sub k pairwise disjoint? Not at all. In fact, they all intersect at the point 0. So nope. You could just take 2. You like B naught intersect B1 is B naught, and that is not the empty set. It's the set that contains 0. So, I mean, you could just give a counterexample like that to prove that they're not pairwise disjoint. You only have to find 2 that have different indexing numbers who have a non-empty intersection to disprove disjoint. So again, a slightly different picture on the notes that are posted, because I drew this picture here, but I drew it again. So because I didn't want to give away the farm by showing you this picture, because the other answers were already on there. So that's B sub k. Let's do one more, and then we'll talk about partitions. But I've carefully, believe it or not, and I'm sure you believe it, carefully selected these examples, these particular examples, to try to reveal different properties that should become apparent as you work through WebAssign and the special homework. Okay, the last one that we're going to do is let C sub j be the set, square bracket j, comma, j plus 1 soft bracket. And this is where j is equal to 0, 1, 2, 3, dot, dot, dot. Okay? Find each set, use interval notation. And then there'll be the question about pairwise disjointness. All right, so A, we're going to make this one a little shorter. The union from j equals 0 to 2 of the C sub j. B, the intersection from j equals 0 to 2 of the C sub j. C, the union from j equals 0 to infinity of the C sub j, right? And D, the intersection from j equals 0 to infinity of the C sub j. Okay, and I've got a picture for you. You probably, want to get in the habit, you don't have to use a bunch of colored pencils or anything, but you'll find it helpful, I think, to draw pictures. You see, our first example, the ace of eyes started at 0 on the left, but C sub j is different. The left bound of C sub j is not a shared value. It's j. It's specific to j. And then we're going up to j plus 1. So C0, right? When j is 0, it goes from 0 to 0 plus 1, which of course is 1. Square bracket on the left, soft bracket on the right. So this is C0 here. C1 is 1 to 2. Include the 1, don't include the 2. C2 is in green. Oh, this isn't C4, is it? Oh, so the extra page of notes has a typo on it. Sorry, change it to C3 if you ever download those. C3 is 3 to 4. Okay. So you can see that way we can kind of see what's going on. Now, is there any space between these sets, like these adjacent sets, like C0, C0 and C1? Is there any space between them? Are there any real numbers that are stuck in between them? Think
No.
about it. Yeah, no, right? Because C0 sneaks up to 1, gets as close to 1 as you want, doesn't reach 1, but is anything that's less than 1 and greater than or equal to 0. Whereas C1 picks up right after that with the 1. So these are kind of continuous as a group. So if we take the union of C0, union C1, union C2, what do we get, folks?
0 to 3, not including 3.
That's right, because we're not leaving anything out. What about the intersection? From 0 to 1, intersect from 1 to 2, intersect from 2 to 3. With these, square brackets and soft brackets as indicated. Are there any values x that are in all of those?
No.
There's not even any overlap, right? So it would be the empty set. What about if we go to infinity from 0, 1 exclusive, union square bracket 1, 2 exclusive, union square bracket 2, 3, keep on going forever. What does that turn into?
0 to infinity.
Yep, 0 to infinity. And of course, if we do this intersection with more and more sets, does it ever get any better? Does that help us find any elements that are in all of those? And it's already a fail just from the first two, right? The intersection of the first two sets is empty. Adding a bunch more to the intersection is not going to help. So are these sets mutually disjoint or pairwise disjoint? If you take any two of them, do they have empty intersection? If you take these two and look at their intersection, is it empty? What about these two? What about these two? What about these two? What
Yeah.
about...
They are disjoint.
Yeah, absolutely. That's exactly right. They are mutually disjoint. CI intersects CJ is empty whenever I is not equal to J. As long as you're not using the same set, the intersection is going to be empty. Good. All right, so that's three nice examples for the index union and intersection game. And there's a reason for the game because we need this when we start talking about the partition of a set, and that's the next game. Any questions before we move on to partitions? All right, partitions. Partitions are important. We've already seen some partitions. We've partitioned Z, pick a divisor D, and then group up integers by the remainder that they, yield when you divide them by D. That split up the integers into remainder classes, right? Remember those pictures of Z, with it sliced up into pie shapes? Well, that was a partition of Z. It's the most famous partition of Z of all is a remainder partition. So given a set a collection of subsets of A, let's say C equals, we'll just do it for a finite collection, but you can do this for an infinite collection too. A1, A2, dot, 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 say A sub n, is a partition of A if all of the following hold. We've got three properties. They all have to be true. One, each A sub I needs to be non-empty. This is for 1 less than or equal to I less than or equal to n, but if this was an infinite collection, it would be for all of them. Two, they have to be pairwise disjoint from one another. In other words, A sub I intersect A sub j needs to be empty whenever I is not equal to j. So that's the pairwise disjointness. And then three, if we take the union from I equals 1 to n of these A sub I, it gives us all of A back. So A is the union of all of these. Let's look at an example. We're going to look at a finite example and an infinite example. We have enough time for just a couple of examples. All right, let's look at a finite example. So let's let A be the set of integers between 1 and 10 inclusive. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 are all in there. Okay? Consider this collection of subsets of A. Here's our collection. It's a set of sets. So the elements are going to be sets. They're going to be subsets of A. The first subset, the first element has the odds 1, 3, 5, 7, and 9. We've seen this set before as a complement, I think, of something else. Then the next element is the set containing 2 and 4. And the last element of this collection is the set that contains 6, 8, and 10. Okay. Verify that curly C, this collection, is a partition of A. So we're going to verify that this collection satisfies these three properties. Okay. If you want, you can think of this set as being A1, this set being A2, and this set as being A3. Okay. You can think of it that way if you want to. All right, so one. You can just do that by inspection. We need each of these subsets to be non-empty. They are all non-empty. So all the subsets in C are non-empty. You can just state that. It'll be obvious. If one is empty, you'll just say, hey, there's an empty set, so this can't be a partition. I mean, it's silly to include an empty set in the collection that you're trying to use to split up a set because it doesn't contribute anything to the union when you try to build the set back. See, when you try to build the set A from the union of all these little subsets, it's silly to have an empty subset. So it's just verboten. All right, two. Now we are going to check that these three sets are pairwise disjoint. This takes a little doing because we have to compare them, not the intersection of all three at one time. We have, because that intersection of all three at one time can be empty, whereas two at a time might share an element. There's a big difference between pairwise disjoint and the intersection amongst them all. It's a lot harder to get an element in all of them than it is to get an element in two of them. See what I'm saying? Does that make sense? Okay, so we're gonna let's check the set containing 1, 3, 5, 7, and 9 intersected with the set that contains 2 and 4. Clearly that is empty. Then we just do it again. The set containing 1, 3, 5, 7, 9, except now we're going to intersect it with the set containing 6, 8, and 10. And it's just a quick check. Yep, that's empty. And then finally, the set containing 2 and 4 intersected with the set containing 6, 8, and 10. That intersection is empty. So we have just verified that they are pairwise disjoint. So we have to do every possible pair. Finally, is the union of these three sets all of A? Well, let's just take a look. If we union together all these three sets, well, these three sets, not about all, but these three. And that is going to have every single element. So basically what we're doing is we're checking that every element of A appears exactly once in one of the three subsets. That's kind of the short check. Every element of A needs to appear exactly once. Questions? Okay, so we'll keep this definition handy, but now let's look at an infinite example. And again, we're going to be asking the question or answering the question about a particular collection being a partition. So I'd like to look at, like I said, an infinite example. So just imagine that this is an infinite collection, okay? And this would be an infinity here. All right, so we're going to let A be the set from 0 to infinity, not including 0. Consider this collection of subsets of A. This collection is a set of sets, we'll call them A sub k's, such that A sub k equals, I've got a typo in the notes, is equal from k to k plus 1. I forgot to put the A sub k equals for k equals 0, 1, 2, dot, dot, dot. I forgot to put this. I'm going to have to replace that page of notes tomorrow. I think the notes just says A sub k such that this, so this should be an equal. Anyway, there it is, correct for you. All the typos get corrected by the time you see the notes. All right, so is curly C a partition of A? In particular, for each of the three properties, either verify, C has the property, or show it doesn't have the property. All right. So let's take a look. So our A is from 0 to infinity, and A sub k looks like k to k plus 1. I do have a picture for you. So I drew this one up too. I can find my page of pictures somewhere where you could draw it. Hmm, where did I put my page of pictures? Would it get lost over here? Well, maybe we should just draw it. Oh, here it is. That's what they look like. All right, so let's check. First thing that needs to be true is each A, we're going to check each of the three properties. Is each A sub I not empty?
Yes.
Yeah, each A sub I's got a number in it. And in fact, you could argue that for A sub I, the number I plus 1 divided by 2, the number that's right in the middle there, the average of these two, which is I plus 1 divided by 2, or k plus 1 divided by 2, is an element of A sub k. The number that's right in the middle. There's a number in the middle of each of these, the average. Okay, like, 0.5, 1.5, 2.5, whatever. All right, so they're each non-empty. Now, are these pairwise disjoint? Is A sub I intersect A sub j empty whenever I is not equal to j?
Yes.
Yes. So how do we argue that? Right. Well, I mean, the worst case scenario is if they're consecutive indexing numbers, like that's the closest they could be together. But look, A0 doesn't include the right bound 1. A1 doesn't include the right bound 1. Even if it did, they still would have an empty intersection. But there's actually some space between these two, namely the space where the 1 is. So I'll show you how I wrote it up in a minute. But the answer is yeah, they're definitely pairwise disjoint. Now, the last question is, if we take the union of all of these A sub i's, just imagine this keeps going forever, because it keeps on, it's an infinite collection. Would that union be A, which is the real numbers that are strictly positive? They start just to the right of 0. Would every real number land in one of these?
No,
Why not?
because one, like the one isn't included, then two isn't included, then three isn't included, and so on.
That's right. We're missing all the integers. Very, very, very astute. So, I mean, like, how do we write this up? Well, you could say A sub k is not empty because just take the average, or you could say k plus 1/2, is in there. You could do it that way, or, k.5. Pairwise disjoint, if j is not equal to k, then this, has no elements. Even if j plus 1 is k, even if this and k are the same, they still don't share any endpoints. And the union of all of these, is it equal to A? Nope. Because when we union them up, what do we get? We get the positive reals minus the positive integers. None of the positive integers are included. They're the ones that are missing, right, where the endpoints don't intersect. So this would be the way to write that union, and it's not all of the positive reals. Okay, questions? These are kind of fun. I think that you'll enjoy the homework. I need to put up an extra credit problem and maybe correct the notes. I'm going to remove the pen here. Nobody's got any questions. See what the gallery's got to say. Um, Any comments, questions, concerns? Okay. Well, I mean, we had a choice, when I designed the semester, uh, have the test before Thanksgiving or have it right after Thanksgiving. And I didn't want people spending their Thanksgiving break studying, right? You need a little break, right, before we have that last final push before the final. So we'll have that test on the Monday before Thanksgiving break. I assume that I assume y'all are on the same break schedule that we are. We get Wednesday, Thursday, and Friday off for Thanksgiving. Good. Everybody's going to need it, right? So you'll get a true break. I'm not going to try to start new material. We're going to cover chapter 7 next week on functions. That will be on the test. So the test is going to be on chapter 5.2 and forward, right? But we still have to understand sequences. So, because you're going to see some sequences come back to haunt you with special homework 10. Um, so chapter 5, chapter 6, and chapter 7. So we'll do 7 next week. Okay. And then we'll have a test, and then we will be almost there. One more week of class. So I have not gotten any emails from folks from Tune. So email me and let me know if you prefer to have your final on Friday or Monday of finals week. Okay, just shoot me an email, please. All right, thanks. Hope everybody has a good night. Stay warm out there. It's getting chilly. I'll stop recording. You too, Eric. Thanks.